Okay, so moving forward to the next idea in this particular chapter, and that idea is change of state. Now, change of state really means that we'll be studying changes from solid to a gas, gas to a liquid, and then liquid to a solid, then gas to a solid, and then solid to, oh, I just wrote it, the other way around. But yeah, the idea is solid to liquid to gases. Okay, so solid to gases, gases to solid, solid to liquid, liquid to gases, gases to liquid, and then liquid to solid. And all of these processes by the name of boiling points, melting points, freezing points, condensation, sublimation, and all that. Okay, now the first idea that we need to study is something that we call as melting point. Okay, and the idea is you go from a solid to a liquid state, right? And if I were to show you this in terms of particles, so that is something like this. Solid has this structure, okay, right? And liquid is a structure like this, a disordered, not that ordered, or whatever wording you want to use. So this is the idea that we are going from a solid to a liquid. What we need to understand here is that what are the energy changes that are happening, because this particular chapter is purely related with what are the energy changes that are happening when changes of states are happening, right? That's the idea. So let's go down in this part a little further. Okay, so when you're talking about melting points, so the idea is we might have an ice, an ice solid, which is of course water in a solid form, and we are taking it into a liquid form or liquid water, right? My, do not judge my drawing, but yeah, that sort of form. And we need to understand what are the energy changes that are happening in this particular process. Now, we're not using the example of water in this case, but what we're using is the example of another substance that you will study later on in chemistry, and that we call that particular thing as isocene. Okay. For now, what you need to do is ignore this part. Okay, ignore this particular part. Do not, you know, focus on this one for now. Even on this, not on this one. Yeah, we are only relevant till here right now. Now, what you're seeing on your board is something that we call as a heating curve. A heating curve is another terminology for energy changes that are happening when you're going from a solid to a liquid. Okay, now understand this. We are studying this energy change for another substance we call as isocene. Okay, this is some organic substance. We're studying this for isocene. So we have isocene solid. Okay, we have an isocene solid, and we need to convert that isocene solid into a liquid. And in that conversion, we need to understand in terms of energies, in terms of kinetic energies, in terms of thermal energy, which is basically heat energy, that what are the changes that are happening. Okay, so let me start from this point. Point number one. Okay, from, let me call this point A, let me call this point B. Okay, now from point A, when we start at this point, understand the process here. What's really happening is that you have a solid isocene material and you are heating it actually. Okay, you have a flame here like this and you are heating it. Okay, so what you're basically doing is you're providing thermal energy or heat energy to this particular substance, right? That's what we're doing when we're heating. When you're making pasta, when you're making some biryani, that's what you're doing, right? You are heating it. Heating really means that you're providing heat energy to that particular substance, to your biryani or to your pasta. Okay, in this particular case, we have what? We have an isocene substance. So by flaming it, by heating it, what we are doing is we are providing thermal energy to this particular isocene substance. Now, what I'm trying to make you understand is what are the energy changes that are happening from point A to point B. So let me also write that down. I'll just erase it from here. Okay. So what we're understanding is what's happening from point A to point B. So what you have is a solid isocene material or a substance. I'll draw it here. You have a solid isocene, and you are heating it with a flame. Okay, this is a flame. Now, what you're doing basically is providing thermal energy to this particular substance. So the first thing that is happening is that you are providing thermal energy. Okay, you are providing thermal energy from point A to point B. You are providing thermal energy to the isocene material. Now, the second thing that you need to understand is that this is a solid particle, right? And if you remember in terms of movement, what we study about solid particles is that solids have vibrations. Okay, so the particles in this isocene material, the particles like this, are already vibrating. Because why? Because all the states of matter are always in a constant random motion, so they are vibrating. Okay, the particles inside the isocene material is vibrating, but when you provide it with energy, with more energy, so what's basically happening? They gain more energy. They already have some energy, very low energy, but when you're providing energy, of course, you have low energy when you're providing more energy, so of course the amount of energy rises, right? It increases. So the amount of energy increases, and these particles are now gaining thermal energy. Okay. Now, when they are gaining thermal energy, what's basically happening is that their movement or their vibration is increasing. So the first point is, you're providing thermal energy. That thermal energy is basically doing what? That is being absorbed by the particles, absorbed by the particles, and their movement is increasing. Their vibrations are now increasing. They're going much faster. So the vibrations increase. Okay, that is your first point. What's the second thing now is happening? The moment when vibrations increase, that means the movement is also increasing. And I told you, whenever you study the word movement, the second thing that should come to your mind is kinetic energy. So if the vibrations are increasing, that means the kinetic energy is also increasing. Okay, the kinetic energy is also increasing. And when the kinetic energy, now this is important, because kinetic energy has a direct relationship with one thing, and we call that thing temperature. This here is a sign for direct relationship. Okay, kinetic energy is directly proportional to temperature. What that means is that if kinetic energy increases, the temperature is also going to increase. If kinetic energy decreases, the temperature is also going to decrease. In this particular case, what's happening is that you're providing thermal energy. That thermal energy is being absorbed by the particles. Now, because they are now absorbed by the particles, so the movement or the vibrations are now increasing, and because of that, kinetic energy is increasing, and because the kinetic energy is increasing, the temperature also increases. That's your whole story of what's happening from point A to point B. And even if you look at this graph, what you'll understand, you have temperature on the y-axis, and on the x-axis you have time. So if you look at the graph that is going upward for temperature, that's what we are also establishing, that temperature is increasing, and that's what also the graph shows you, the temperature is increasing. So from point A to point B, the whole process is that you're providing thermal energy to this isocene material, and because now the particles have more energy, the particles are absorbing energy, now they have more energy, and because they have more energy, the vibrations or the movements are increasing, and because that is increasing, the overall kinetic energy is increasing, and the temperature is increasing. So there are 4 points in total. Thermal energy, you're providing thermal energy. Because of the thermal energy that you're providing, that thermal energy is being absorbed by the particles, and because the now energy has increased, so the movement is also increased, or the vibration is also increased, and movement of vibration is directly proportional with what? Kinetic energy. And when kinetic energy increases, temperature also increases. That is the entire process that is happening from point A to point B. Okay, I hope that is clear. Now, let's look at point B to point C. This particular point. One deduction you can make already is that because this is a temperature based graph, you can see temperature is rising at this point, but at this point it has remained constant. So you already know that from point B to point C, temperature remains constant. Okay, temperature remains constant. Now let's backtrack this one. Before I tell you anything, you can already make deductions. How? Because you see, what did I told you at the first part? Temperature increases was when kinetic energy increases. So if temperature is not increasing, if temperature is constant, that means kinetic energy is also constant. Kinetic energy is also not increasing, right? Because in the previous part, kinetic energy was increasing and that's why temperature was increasing. And here you can see from the graph, if the temperature is not increasing, that means that the kinetic energy is also not increasing. In this particular case, temperature is constant, that means kinetic energy is also constant. But what we need to understand is why this kinetic energy is constant at this point. Because the process is still happening, right? At this point, from point A to point B, what has really happened is that this isocene material has reached to a certain point, to a certain temperature. And that certain temperature is 37 degrees centigrade, which is actually the melting point. So at 37 degrees centigrade, the solid isocene substance converts to liquid isocene. Okay, now let's understand the moment it reaches point B, which is at 37 degrees centigrade, which is the melting point. Now we need to understand what really happens after that. So from point B to point C, the process is still the same, right? You're still providing thermal energy, but now at this time, what's really happening in the first part? What was happening? You were providing thermal energy. That thermal energy was being absorbed by particles, and because of that, vibrations were increasing, movement was increasing, and kinetic energy was increasing. Now at this point, you're still providing thermal energy. Okay, you're still providing thermal energy, but now this thermal energy is not anymore being absorbed by these particles. Okay, because they already have enough energy, right? Now what's really happening is that you're still providing thermal energy is still being gained, but it's not being absorbed by particles. But what are they using it for? They are using it for breaking the forces of attraction. Remember, I told you, you see, this point you've got very high forces of attraction. That's why these particles are attached to each other. So to reach this point, what you have to do is to break these forces of attraction. So once they reach a temperature which is 37 degrees centigrade, now what's happening? Whatever the energy that is being still provided, that energy is being used to break these forces, to break these forces of attraction. So particles are now using this thermal energy to break free from these forces of attraction and to convert themselves into a liquid state. Got the idea? Okay. So now thermal energy, it's being used to break the forces of attraction, FOA, and the moment the force of attraction starts to break, what really happens? The ordered manner, the structured manner starts to break. Now you have a disorderly manner, right? You have a disorderly structure, disorderly manner, and the other thing that is happening is that you can say that now you don't have, you can say, a regular pattern arrangement. You have a disorderly manner. I think it's the same thing, right? Yeah, but the next thing is that now you see the correlation was particles were absorbing energy here, and that's why vibrations were increasing. Now because the particles are not anymore absorbing energy, and that's why vibrations are not increasing, that's why kinetic energy is also not increasing. So kinetic energy remains constant, hence temperature also remains constant at this point. Okay, that is your idea. If kinetic energy was changing, which is in this case not, if it was changing, then the temperature would also change. And one very important point, at this point from point B to point C, you need to remember that you will have both liquid isocene and solid isocene. At this point, from point B, starting from point B, not all of the material has melted or converted into a liquid. It's a mixture, right? It is, you have solid as well, and you also have liquid. So at this point, you have what? You have a solid plus liquid mixture. Okay, I hope you got the idea. Then let's go from point C to point D. Now this is interesting. It's not interesting actually. What I'll just say, point from point A to point B and from point C to point D, it is entirely the same process. Only difference is point B to point C. Now from point C to point D, the same things are going to happen again. Why? Because the moment you reach point C, remember, point B, you had a mixture of solid and liquid, but the moment you reach point C, now all of the solid has melted into liquid isocene. Okay, you don't need to, you don't have any more solid. At point C, all of the solid has melted. And now the minute all of the solid has melted, the same process starts to repeat. And what is that process? So at point C to point D, at point C, all has melted, you know, all solid has melted, and the same thing flows again. Why? Because you're still providing energy, which is thermal energy, meaning the burner, the flame is still on. You're providing thermal energy. That thermal energy again is being absorbed by the particles, right? It's been absorbed by the particles, and because of that, what happens? Vibrations increase, vibrations increase, and then because of that, kinetic energy increases and temperature again increases. And you can also see that from the graph. You see, temperature is increasing. Okay, and you might have this question that, oh, why are now particles absorbing energy again? Why weren't they absorbing at point B to point C? Because you need to remember, there are certain temperatures where these things melt or where these things freeze. So at those temperatures, the particles do not absorb energy. You see, till it was at 37 degrees centigrade, there was no energy at this point that is being absorbed by the particles. But the moment it goes from it reaches point C and it starts to go upwards, now what you have is that thermal energy is again being absorbed by the particles, because a state change has happened, right? Previously you had solid particles had a melting point. Now what you have is, at point C, what you have is liquid particles. Liquid particles will have some other breaking point, and the breaking point for liquid particles is basically the boiling point. So the moment they reach a temperature which is the boiling point of this liquid isocene material, they'll also follow the same process. They then they'll stop absorbing energy. The moment they reach the boiling point, at this point, this is not a part of slavery, that's why I'm not getting into it. But the moment these liquid particles reach at this boiling point, then this whole process will follow again.